Here we are at the warm-up for the 1.3 set of notes. We're asked to graph this line y is equal to 2. And as you guys recall from algebra, that's just simply a horizontal line at 2. So you should see something like this. And then down a little bit further, we're asked to find that limit. The limit as x approaches 4 of that function 2, that one that we just went ahead and graphed. Now, since we have this function, y is equal to 2, and we have this limit that we're looking for as we approach, as x approaches this value 2, we know that from our 1.2 set of notes that it has to actually satisfy that the limit as x approaches 4 from the left side of our function must be equal to the limit as x approaches 4 from the right. Again, that was from our 1.2 set of notes. So our limits should end up matching and ending up at the same spot. Well, let's go ahead and just look at our graph and see if that happens. So as you approach 2 from the left of our function, we see that we end up with this limit of 2. Likewise, if you approach 2 from the right, we do in fact meet up at that specific limit of 2. So then to answer that question, since they do meet up at the exact same spot, the limit as x approaches 4 of 2 just comes out to be 2 itself. Now this paves the way really well for our theorem, where it asks for any constant c and any real number a. As long as we have the limit as x approaches some constant number of a, and a just happens to be a real number, then we end up with just the actual value a. Alright? So again, this was a prime example of that. We had the limit as x approached some constant number of a real number, in this case 2. It just came out to be literally the same exact thing. And again, here is our graphical representation of that. So this is known to be one of the most easiest types of limits anytime you're approaching some just real number. In other words, there are no real x's to plug in anything. You don't even really have to do direct evaluation. It's literally just you have the limit as x approaches some constant number of just some number is equal to that same number. All right? And so just another little quick example of what that could look like is if, for example, we have the limit as x approaches, we'll go with 5 of some constant number 7. Well, the limit as x approaches 5 of our constant 7, well, because this is our function 7, that line y is equal to 7, that's never going to change. It's always going to be 7, no matter what x value you're talking about. And as a result, it just comes out to be 7. So again, one more time, that is our warm-up and theorem from the 1.3 set of notes.